In this section we're going to have a look at Monte Carlo type methods. So first of all, Monte Carlo methods are used for solving so-called forward problems in UQ. A forward problem is quite simply taking a parameter, applying some kind of a model, and then typically doing some post-processing. In contrast to that, inverse problems would be referred to when you have given measurements, for example, and through basically inverting your model application, trying to get back to what the underlying parameters would have been. We'll cover that later though. So here we have a look at going from parameters to some model state to some derived quantities. And what that means in practice would be something like you might have a parameterization of maybe a ring structure for an aircraft. Your model state might be a simulation result, including all vortices of maybe some kind of an maybe a Stokes flow equation or something, possibly coupled with the airframe itself, so potentially something quite heavy. But then typically you're not interested in each and every bit of airflow around an aircraft, but what you're actually interested in is it safe to fly? So typically you still have some kind of post-processing to get to some quantity which you are actually interested in, and I'm going to call this derived quantity here. Note that quantities of interest play a much bigger role in inverse problems. In principle here we could just say we map from parameter all the way through the derived quantity, but I think it makes sense to distinguish the two just to essentially segregate the actual modeling and post-processing essentially, because in practice that's also what you would do. Now, having so far a deterministic model mapping from parameters to some quantity we are interested in is nice, but for many applications it's just not good enough. So when you look at this forecast of a hurricane, for example, you can see that there's not just a single trajectory being given, but rather an entire spread. And you can see that over time, the spread actually increases. And the reason for that is that not everything about this system is entirely known. In fact, weather simulation are notorious for this and kind of chaotic anyways. But the main reason is actually that you just don't have enough data about the current state. You can't measure each and every bit of air pressure in the entire area, for example. So this lack of information translates into an uncertainty in prediction. Of course, we do uncertainty quantification, so that's what we are actually interested in here. And there are many other applications where this happens. Measurements might be inexact. Measurements might be only available in sort of a statistical sense, so maybe you get an expected value. There may be even certain things about reality where things are actually inherently random, so you cannot have that single accurate measurement, but it's actually just nature rolling dice at certain points, and we'd have to represent this in a way. So how can we represent these uncertainties and random behaviors? Well, the idea is, first of all, rather than having just a deterministic model mapping from a single parameter to a single prediction, we replace our parameter by an entire parameter distribution, so as in a statistical distribution. Now, of course, when you apply the model, we do not only get a single prediction for our model state, but rather we get an entire distribution. And then typically you're interested in something which is derived from your distribution. So a typical thing you might be interested in is maybe some expected value, or in case of the aircraft, what is the likelihood of the airframe being safe, or in case of the hurricane, maybe what is the likelihood of certain cities being hit, which is of course a much lower dimensional entity than the actual distribution of all plausible trajectories for this hurricane. So how can we solve such a thing? Clearly it's a bit challenging because rather than having a potentially very complex PDE, or model in general, we now have this sort of additional dimensionality of uncertainty, because we may also have quite a lot of uncertain parameters, etc. For now, we are going to stick with a very simple approach, though, just to get started. When you dumb it down, you can even solve these problems on paper for extremely simple cases. So let's say our parameter distribution is just a Gaussian distribution, and our model is quite simply taking the parameter, adding 1 to it. And we say that what we are interested in eventually is the expected value of that model prediction. So for this extremely simple model, we can say, well, pi is a standard Gaussian, so the distribution of f is actually also a Gaussian distribution, only with a shifted mean. And the quantity of the derived quantity that we're having a look at here, just being the expected value, is in that case clearly just a 1, namely the mean of that distribution. That's fairly easy, but of course you can think of a lot more complex things, and quite clearly you cannot represent a hurricane by a model that simple. Also, parameter distributions might not just be Gaussians, and the derived quantities, of course, even the post-processing may be something much more complex than just, for example, taking single point values or something. They might themselves be, in the worst case, maybe even coupled to other models as well. So, how do we actually get to this in a more general case? And the Monte Carlo approach is one which is quite universal and in principle very easy to understand. The idea is we just draw samples rather than wanting to represent the entire distribution being mapped through the model, leading to something very complex if you want to do it analytically, assuming your model is something very complex. We instead withdraw to sampling. So the idea is we just draw samples from our parameter distribution, essentially rolling dice. And for each parameter we get, we apply the model. And because, since we are sampling from our original parameter distribution, these samples have that distribution. Likewise, the model applied to these samples will lead to a set of samples, this time samples in state distribution, that just match the distribution we are looking for. And then we can, of course, still do some post-processing afterwards to get our quantity we are actually interested in, like a certain likelihood of an F-ray being safe, for example. In case of just wanting to achieve an expected value of the model state distribution, that is quite simply taking the mean of the samples that we have. Because these samples are already from the right distribution, there is no weights attached. This is fairly easy to do. Now that's all good, and in principle you can essentially solve any forward UQ problem that way. You may have noticed though that the uncertain parameters themselves could be very high dimensional. For example, in the hurricane case, parameters that go into your model would be some starting condition involving possibly pressures across the entire surface of the area. And that's something you obviously don't have, but that you might have to represent in a rather fine-grained way to accurately represent the chaotic behavior of this hurricane. So you can see that this parameter distribution itself could be very high dimensional, and drawing samples from that distribution and trying to cover sort of the entirety of this distribution may require quite a lot of samples, and each of these requires you to run a model for in this approach. So you can see that this can become very costly soon, and this is why there's an entire zoo of methods which try to come up with more efficient ways of sampling possibly, or even going into a more, well, sort of intrusive way if you look at it from an engineering perspective essentially, where you try to modify your model such that it already caters to some of this pushing forward of distributions. And in that case, like for example for polynomial chaos approaches, you can get some very efficient methods, at the cost of having to modify your model quite heavily. And some other approaches may also require Jacobians of your model with respect to parameters, of course, which for some models can be very easy, but for example, for some nonlinear PDEs or something, those can be very complex indeed. So you can see that there's an entire range, and it's always a bit of a balance between efficiency and, well, on the other hand, also, of course, the burden of implementation that you have to do. And for some methods, or for some models, it may actually be impossible to apply the most efficient methods quite simply because they require too much knowledge about the model itself. Alright, so let's proceed to the software side of things. In the Python example code we have for this Monte Carlo approach, we first of all begin by defining a very simple model, namely the infamous banana distribution, quite well known. The idea is that this just takes a point in two-dimensional parameter space and maps it to a different one, leading to a sort of perturbed shape. Now, applying Monte Carlo to this essentially means you could draw parameters from, for example, a Gaussian standard Gaussian distribution, apply the model, and look at the resulting samples in state space. So what this code does is the usual steps to include your MUQ instance. Always remember to add up this path so you'll actually find your personal installation of MUQ. We get the packages we need. And one thing we always need for, or we need for quite a lot of MUQ applications is random number generation. So this here is just a very brief example of showing you how to get to a bunch of random number generators provided by MUQ for various distributions. And here we also have some nice plots to show what the results look like. So this is a very basic building block you can use in many places. Now, building a model has already been introduced. And this is quite simply implementing that banana distribution shown at the top. So eventually this means in the evaluate function, you implement the particular formula given above in this example. In more complex problems, of course, here you might be actually solving a PDE, combining multiple of these mock pieces to something more powerful, etc. Now, actually doing the sampling is fairly easy. What we do is we get ourselves an instance of our banana transformation. We also generate a bunch of random numbers with a Gaussian distribution, or actually two-dimensional random parameter vectors. And what we do for Monte Carlo is quite simply taking these samples and applying our model to it. And you can see that the result is now actually distributed according to this banana density as expected. You can apply the exact same approach for more complex models. And here we're going to have a look at the Poisson PDE example, which we have seen before in the modeling part. So this is a code that you should already be familiar with from before. Just again copied in here so we have the model available. Getting to the distributions we are interested in, but in this case we say we have our parameterization of the KL expansions, and we want to plug in Gaussian distributed coefficients for those. And what we're interested in the end is the distribution of PDE solutions as our state space. And finally, in this example, what we do is we have a look at the PDE solutions at a certain point. And the quantity we are eventually interested in is the distribution of PDE solutions at a certain point in space. So this is again doing the same thing, taking samples from our Gaussian distribution, and applying the model, saving the results. Once that is done, we can do some post-processing. And that means we can define a certain index for a node where we want, for a node in the PDE discretization where we want to access the solution value. And we do that for all the samples that we've got. And then, for example, you can compute a mean value on that. Or, and doing this in a more general way, plotting all the results in a graph and having a look at the distribution of the derived quantity. So what you see here is the distribution of, it's actually samples from the distribution of our conductivity field, depending on the Gaussian parameter we plug in the first place. This is sort of the intermediate step. And then what the PDE model gives us is, for each of our samples, one PDE solution. And as our derived quantity, we have a look at the solution values at a certain point in the domain space of our PDE. And you can see that these, again, have a certain distribution. And when you plot the histogram, you see that this is quite resembling of something like log Gaussian, possibly. But most importantly, you can see here that this is not just a shifted Gaussian, so we have already a slightly more complex model in this case. And then for later, of course, you're very welcome to use the time we have in the practical session to just modify all sorts of things about this algorithm, plugging in different models, changing the model itself, changing the derived value you're interested in, or maybe even trying to take an existing model that you have and applying Monte Carlo to it. Alright, so thank you very much for listening, and we'll continue on with the practical session.